Imagine a metal fabricator in Kotway building a 1 meter by 1 meter square window frame. To keep the structure rigid, he needs to weld a diagonal crossbar across the middle. Looking at this geometric layout, Pythagoras' theorem dictates that the exact length of that diagonal is the square root of 2 meters. If our fabricator types that into a calculator, he gets 1.41421356, and the sequence goes on forever. If he chops off the decimal and cuts his metal at exactly 1.41 meters, the bar will be slightly too short and the window will lack structural integrity. To maintain absolute precision, mathematicians and engineers stop relying on decimals. Instead, they leave the number written exactly as a square root. We call these exact, never-ending roots surds. This split-screen comparison shows an important distinction. Not all square roots are surds. On the left, the square root of 9 is exactly 3. That is a clean rational number. But on the right, the square root of 10 creates an unending decimal. It is an irrational number, and therefore it remains a surd. To achieve true structural precision, we have to put the calculator down. We need to learn how to manipulate these irrational roots directly. We start by simplifying them. Take the square root of 20. We want to find the largest perfect square factor hiding inside that 20. If we look at the list of factor pairs below it, we find 4 and 5. 4 is our target perfect square. We can rewrite this as the square root of 4 times the square root of 5. Since the square root of 4 is exactly 2, that value moves to the outside of the radical. The 5 is not a perfect square, so it remains inside. Our simplified expression is 2 root 5. When adding or subtracting surds, you treat them exactly like algebraic variables. Notice how 2x plus 5x equals 7x. In the exact same way, 2 root 3 plus 5 root 3 equals 7 root 3. A common error is trying to add different roots together. You cannot add root 2 and root 3 to get root 5, just like you cannot combine an x and a y into an xy. Before you can add or subtract any surd expressions, the numbers inside the roots must be perfectly identical. This strict rule makes a problem like root 50 minus root 8 look impossible to solve at first, because the numbers inside the roots do not match. To find a common root, we must simplify both terms. Pause the video here and extract the perfect square factors from both roots before attempting to subtract. Root 50 contains the perfect square 25, which simplifies to 5 root 2. Root 8 contains the perfect square 4, which becomes 2 root 2. Now that we have exposed the identical roots, 5 root 2 minus 2 root 2 leaves us with 3 root 2. Multiplication follows a different set of instructions. Unlike addition, you can multiply any two surds together, regardless of the values inside the roots. To solve this, you multiply the outside whole numbers together, and then multiply the inside roots together. 3 times 4 gives us 12 on the outside. 2 times 6 gives us 12 on the inside. Because multiplication bypasses the rigid matching constraints of addition, isolated surds can interact directly to form entirely new mathematical expressions. There is one final rule to master. In mathematics, leaving an irrational root in the denominator of a fraction is considered an unfinished expression. To fix 10 over root 5, we have to rationalize it. To eliminate that root without changing the value of the fraction, we multiply both the numerator and the denominator by that same root. On the bottom, root 5 times root 5 is the square root of 25, which is a whole number 5. The root is gone. Finally, 10 divided by 5 leaves us with the simplified expression 2 root 5. This chart summarizes the core mechanics for surds. You simplify by extracting perfect squares, add or subtract only when roots match, multiply outsides with outsides and insides with insides, and rationalize to clear denominators. You should take a screenshot of this summary grid now. It provides the exact steps needed to solve any surd operation in the syllabus. Mastering these operations means you no longer rely on rounded decimals. You can carry the exact value through every step of a calculation, maintaining the level of precision required by architects and engineers.